Okay, let's take a look at the calculus stuff we did today. We talked about some of the properties of limits, and then we talked about analytical or algebraic limits. So again, we're going to go ahead and take a look. I'm going to walk through the example we did in class. The examples, I'm going to kind of jump around a little bit. So I gave everybody this handout about the properties of limits. Basically, if you read through these, it gives you some rules you're allowed to do to kind of simplify the computation of limits. So, I mean, I'm not going to go through all of them. I'm just going to kind of focus you as we do some examples where we apply those. So, for example, let's kind of zoom in here and we say the limit of f of x, the sum of f of x plus g of x as x approaches 3 from the positive side. This is one of those ones where we're going to be using the sum and difference rule. So the limit of a sum is equal to the sum of the limits. In other words, what I mean is this. I take the limit as x approaches 3 from the right of f of x, and I add that to the limit as f of x of g of x, sorry, as x approaches 3 from the right. And then what I can do is then over here and look, and what I do is I do this problem. I find out that the limit of f of x as x approaches 3 from the right here is 6. As I read this chart, as we get closer to 3, it's 6. As I do the bottom, and I do the same thing, and I approach 3 from the right, I find out that it is, so I'm going to g of x as x approaches 3 from the right, and as we look here, we're up here at 8, because we're not down here. This would be 3 from the left, 3 from the right is up here. That's 8, 6 plus 8, it's 14. So I'm allowed to do that. Instead of trying to combine these two graphs together into one big graph and try and figure out where things are, if I actually were to have combined these two graphs together, what would happen is by adding, I would find out that around 3 on the right side of the graph, this thing would approach around 14. So that's the first one. The next one, again, now this kind of builds in. We got a difference, but we also have a coefficient rule. So what we're going to do is we have this coefficient rule up here. We're allowed to kind of bring the coefficient up front. So the first thing we're going to do is we're going to say that this is the limit as x approaches 5 of 3 times f of x minus the limit as x approaches 5 of 2 times g of x. And then what I can actually do is like factor those coefficients out, if you will. 3 times the limit as x approaches 5 of f of x minus 2 times the limit as x approaches 5 of g of x. And then what I can do is I can go ahead and plug in as I go as x approaches 5 on f of x, as x approaches 5. I go up here and I know that this guy is roughly 2. So this is 3 times 2. Because as we approach 5 as a whole, it's right about there. Now I go to g of x, I do the same problem as x approaches 5. When I look at as x approaching 5, what goes up here? I trace my finger on up 5, and I go up and I see I've got 1, 2, 3, 4, 5. To me, it looks like it's 5 up. So this is 2 times 5. So that's 3 times 2 minus 2 times 5, 6 minus 10. It's negative 4. Process follows for all of these. So now this says the limit of f of x squared. Well, what I can do is actually rewrite this as the limit as x approaches negative 3 of f of x, the whole thing squared, not negative 2, the whole thing squared. And I can go and take a look and see that as we approach negative 3 here, you're going to see that this guy actually approaches negative 6. So negative 6 squared in the parentheses is 36. So what I did there is I used this power rule. I can take a power here and bring it out. Now, radical, there's a radical root rule. If I'm taking a radical of a function, I can then turn that into the radical of the whole limit. So this can become the square root of the limit as x approaches 4 of 5 times f of x. So I can look at this as the square root of 5 times the limit as x approaches 4 of f of x. I'll look at my f of x function as x approaches 4. This approaches 4. So this becomes the square root of 5 times 4. Square root of 5 times 4 is 20. So it's square root of 20. And like I said, we're just going to leave it alone. We're not going to simplify it. We're not going to make that 2 root 5. We're not going to make it a decimal. It's the square root of 20. And then we work through the rest of those. So again, this one right here says the product. So what I'm going to do is I'm going to look at the limit as x approaches 3 of g of x. I'm going to look at 3 times the limit as x approaches 3 of f of x. What I'm going to do is work my way through 3. And the limit as x approaches 3 is 6 times. So that's 18 times. What's going to happen is if you actually go over here and you look at x approaching 3, it's 1 from the left, it's 6 from the right. This is a does not exist situation. So 18 times does not exist. If any part of it does not exist, the whole limit doesn't exist. Last one, the big thing to focus on this one is let's start with the denominator. If the denominator becomes 0, because what I can do is I can actually change this into the limit of f of x, x approaches 6, over the limit g of x as x approaches 6. So first thing I'm going to do is start with the denominator, make sure it's not 0. So as x approaches 6 in the denominator, which would be right, what, 2 4s, 2 4 6 6 right here, trace my finger up. I'm going to find out that this denominator is 5, so I can keep going with it. It's going to give me an answer. When I actually do it on f of x, as x approaches 6, you're going to find out that it's 0, 0 over 5 is 0. So this limit would be 0. So that's our first little bit of properties. Didn't really touch on composites, but what happens in composites is slightly different. So I'm going to do a few of these back here just to understand the product of limits. I mean the limit of composites. So what this actually becomes is I'm going to bring this limit inside. This is going to become f of the limit as x approaches 3 of g of x. And what I'm going to do is I'm going to go and find on the g of x. So let's go over here and look on the g of x function as x approaches 3. 3 is right here. I'm going to find out that this limit is actually 1. So what that tells me is I'm going to replace this whole thing in here with a 1, and this is going to become f of 1. So now what I'm going to do is I'm going to go and use this. There's no limit anymore. The limit's kind of been absorbed. I'm going to come over here to 1 on the f. I'm going to trace my finger down, and I'm going to see that it's -2. So this gives me -2. So what that says is the limit of this composite function is -2. And that process is going to hold true for all of these. So we did some of these in class. We talked about them. The one I kind of want to focus on is this one, because this one had something unique happen. This one says what we're going to do is f the limit of g of x as x approaches 1. And what I want you to look at over here is as we approach 1, from the left, we're getting a -1. So as we're approaching 1 from the left, we're getting a value of the limit of g of x as x approaches 1 from the left is giving me a -1. The limit as g of x as x approaches 1 from the right, so this way, is giving me a -3. It's a -3. So this is giving me a -3. And according to the rules of limits, these two aren't the same. So this guy is technically going to look like it does not exist. However, we're going to take a moment and we're going to go and look at the other curve just to be sure. Because while the limit doesn't exist, what I want you to look at is, I want you to look at what is f of -1. I want you to look at what is f of -3, which is what these two pieces are. F of -1, when I trace my finger down, f of -1 is -6. If I go and I look at -3, trace it down, the function is also going to be -6 there. These two numbers are the same. So technically, while this limit doesn't exist, when I go and I take the composite function, since these two numbers are the same, we're actually going to have a -6 there. So that was one of the things we did during class today. We talked about these composites, and the homework from that was composites. And then the only other thing I want to kind of talk about is I wanted to talk to you a little bit about the other part we did, which is our analytical functions. And what I'm going to do is I'm going to use the notes we used in class so that you kind of see what we were doing. I'm thinking about right now, should I have ready? So what we did today, other than that, was we talked about algebraic limits. Your goal is to always try substitution first. Always, always, always try substitution first. Actually, I wanted to do. Oh, sorry, this is my apologies. This one is the first one. Always try substitution first. So what I mean is plug that 2 in for x. So what I'm going to do is 4 times 2 squared plus 3. 4 times 2 squared is 4. 4 times 4 is 16. 16 plus 3 is 19. That limit's 19. So if I can, if I have nice functions, I can plug in. Look at this guy down here. I'm going to plug in. I'm going to do 3 squared minus 16 over 3 minus 4. This is going to give me -7. This is going to give me -1. Technically, that's the answer. If you want to, you can make it 7 because it plugs in and it simplifies. So, but occasionally, you're going to get problems that don't simplify. And what I mean is, if I go to substitute on this one, if I plug in a 1 in this denominator, what is going to happen is the following. I'm going to get a 0 down below. I'm actually getting a 0 up above too. So what I need to do is I need to do some factoring. What I'm going to tell you is when you do this, the way these are designed, typically, this thing up top is actually going to factor where you're going to be able to take out an x minus 1. Now, I mentioned this in class, and hopefully some of you do remember. There's a trick on cubics on how to do it when you have this kind of perfect cube trinomial. It's SOAP, same, opposite, always positive. So same sign, 1, opposite sign, always positive. That's what it's going to be. If you didn't know how to do that, what I taught was I showed you how to do a quick synthetic division. So what I'm going to do is I'm going to try and get this 1 out of there because of that 1. I'm going to write down the coefficients. This is technically x cubed plus 0x squared plus 0x minus 1. Write down the coefficients 1, 0, 0, -1. Bring the 1 down. 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1. -1 plus 1 is 0. I have no remainder. That would be my, because again, if you think about it, this is the x cubed. This is the 0x squared. This is the 0x, and this is the -1. Everything shifts down 1. This becomes x squared plus x plus 1. And as you take a look at this, the x minus 1's cross off. You're left with x squared plus x plus 1. Now I can substitute in. This becomes 1 squared plus 1 plus 1. The answer on this one is 3. The other one I want you to talk about is here, conjugates, because if I actually plugged in a 5 here, 5 minus 5 is 0. If I put it down below, 5 plus 4 is 9. Square root of 9 is 3. 3 minus 3 is 0. I can't get 0 over 0. The rule is you're going to, what's called the conjugate. I'm going to take the conjugate of the denominator. What I mean by the conjugate of the denominator is square root of h plus 4. Instead of a minus sign, I'm going to put a plus sign. And I'm going to do the 3. Because what's going to happen when I do this multiplication, square root of h plus 4 times positive 3 gives me 3 root h plus 4. Negative 3 times positive root h plus 4 gives me a negative. Those two middle terms will cancel out or cross off. So what I'm going to do is this. I'm going to go ahead and multiply both sides by this root h plus 4 plus 3. Because this actually is 1, if you will. This would cross off. But when I do that, what is going to happen is the following. I'm going to get h minus 5 up top. I'm going to get root h plus 4 plus 3 over. Now here's the trick. The really nice thing about conjugates. When you multiply something by its conjugate, it's basically square each one of these terms. So it's basically multiply this times this. root h plus 4 times root h plus 4 gives me h plus 4. Radical goes away. Negative 3 times a positive 3 gives me negative 9. And if you take a look at simplifying this, h plus 4 minus 9 is now going to give me this. H minus 5. And if you take a look, cancels off. I'm left with root h plus 4 plus 3. And now I can plug my 5 in. Root 5 plus 4 plus 3. Root 5 plus 4 is root 9 plus 3. Technically, on this one, I could leave it like that. It's root 9 plus 3. Or you could call it 6. Or you could call it 6. So that is how we did things algebraically or analytically. I gave a homework, some practices. The big deal is if you can't substitute and solve, you're going to need to do some sort of factoring to solve, kind of like I did here, or you're going to need to do a conjugate thing. So please use the daily reflection to give me some feedback if you have any questions, and be ready to talk to me on Tuesday about this stuff.